What are modules? We have actually used them before, for example, the system module or the pickles module for saving and loading files, binary files, to a computer. They are there for extending the core Python language. Okay, so, and that's actually a principle that exists in most programming languages. That is, programming languages have some core functionalities, like for example, you can make loops using the for command or while command. You have if statements and so on. That's the core of the language. But then everything that goes beyond that is typically separated out in a different part, which is called a module. Okay, and the reason for this is that if the Python language itself would support everything that is available in packages, the core of the language would be huge, right? You might just open Python and use the interpreter to compute a simple sum of two numbers. You do not want to load all the functions that are available, for example, for loading data from files, right? That's just not necessary. So one reason is that we separate out certain functionalities and modules, because otherwise the programming language itself would grow very huge. Right? Secondly, because things are separated out in distinct packages, it is very easy to update a certain functionality of Python. A developer that has written the pickles module might come up with some improvement today, upload it to the web, and you could just download this updated version of the package and could immediately use it without installing the whole Python core from scratch. Right? So having modules makes it very easy to add new features to a programming language and also to upgrade if some improvements are available. And of course, last but not least, the Python core is developed by a very small group of people, right? The core Python development team, which may be about 100 people worldwide or so. I don't know the exact numbers. Whereas there are literally thousands of programmers that provide modules. Right? So having modules makes it very easy to democratize a language, to make others able to enable others to contribute to the language. Most programming languages are extensible. So in Python, we have modules, and in other programming languages, you have similar concepts. For example, packages, which is the term used for MATLAB or in Mathematica, or libraries, which is used in C and PHP. But they all have the same idea. They extend the core programming language with some useful functionalities. Now, what modules are available in Python? It turns out that there are modules which are kind of officially supported by Python, and they are available in the Python module index on the python.org website. So there is a link in the lecture notes. You can just click, and you will find here all the modules that are typically provided with every installation of Python. So these modules should all be available with Anaconda as well, and you should have them available on your machine. So for example, there is a module called email, which can be used to send emails directly from your Python script. That's actually the package that I use for sending you the feedback reports on your lab classes in a week, right? So you can actually use Python to generate emails automatically. Of course, this can also be misused. You can actually send lots of spam messages like this, but you should refrain from doing so. What else have we used? The pickles module should appear somewhere in this list. Maybe not. So pickles seems to be not one of these core packages, but let's look for the systems package. I'm sure it's in the list. So sys, here it is. That's the one that provides the exit function that we have used before. Okay, and so on. So if you're interested, have a look at this. There is also a statistics package for doing computations in stats. There's a string package, and so on. So it's a very long list. But actually, these are not all packages that are available. There is another collection called PyPI. Okay, and this has at the moment 170,000 projects. Typically, each project corresponds to one module. So a huge selection of modules available for us to be used. Okay, which is very nice because it saves us a lot of time and work. If someone else has already implemented what we need, why not just use it? Okay. Of course, some care has to be taken. Whenever you use stuff from the web, there is a probability that there are bugs in it, or maybe it's not doing exactly what you expect it to do. So then the responsibility, of course, is with you to verify that the package that you have downloaded and that you use is actually working as intended. So just to demonstrate how we can use packages, I have picked out a package called iter_tools. That's a package that has many things that have to do with iteratables. Okay, so there is in this package a function called permutations. And what this function does is it takes an iterable as an input. So that could be, for example, a set or a list. And then it returns all the permutations available from the elements of the iterable back to us. So for example, if I call the function with a string input, ABC, then we have already seen when we iterate over a string, what we actually get are all the characters one after the other. So the iterable actually provides the letters A, B, and C, and the permutation function then returns tuples of these three characters being permuted in all possible ways, which in this case would be 6 different permutations. Okay, so permutations returns tuples. If I want to have a list of all the permutations, I need to explicitly convert it using list, because permutations returns an iterator. In the first place, if we want to convert this iterator into a list, we have seen how to do this before, we need to call the list function on it. Right. So that might be an interesting function that we might want to use in one of our programs. How can we do that? Well, for doing this, we need to just import this function into our Python script. And this is done simply by using the import keyword. Import space module name will import a module into your Python workspace, and from this moment on you can use it. So here's an example. I'm importing the package iter_tools, and from this moment on I can access the permutations function that is provided as part of this module. And in order to access it, I need to tell Python where it is located. It's still part of the iter_tools package. Therefore, I need to call it like so: iter_tools.permutations, and then the parameters given to the function. So let's just try this. Here we are. I have now loaded the package, and it prints out all the permutations of the 3 characters A, B, C as required. Now, sometimes this module name is too long to be typed over and over again. iter_tools is already, it's already quite long, too many characters to retype. Therefore, we can define an abbreviation for a module name. For example, IT. That's the name that I came up with. It makes sense to abbreviate iter_tools by IT. From this moment on, instead of typing iter_tools here, I can just write IT, right? And this will now access the iter_tools package. This functionality of having abbreviations is also very useful in some other circumstances. Imagine that we have the possibility to buy a very expensive module from some software provider. Maybe it's a module that does something very efficiently, but we have to pay a lot of money for using it. So that's a module that I call expensive and fast. Okay? But at the same time, we have another module available for free, which does the same thing, but is very slow and inefficient. Okay? That's a module that I call free and slow. Now, you want to use functions in these packages, and you want to have the opportunity to switch easily between both of these modules without rewriting your code. How can you do this? Well, you can do it like this. You can try to import the expensive and fast module and call it some abbreviation, let's say ABBR. If this fails, then we will fall back to the slow and free version by importing this one using the same abbreviation. So after this import in your code, you can call the function always by the same name. You do not need to change the name, even though you're potentially working here with two different modules. Okay? So that's very useful sometimes. And a situation that arises quite often, that you have expensive and fast implementations compared to slow and free implementations available. Often, modules come with hundreds, if not thousands of functions in them, but typically we end up only using one or two of them. In this case, we should not really import all the functions as we have done here. When I typed import itertools, from this moment on, all the functions that are available in the itertools package are at our disposal. Let's have a quick look into this itertools package and see what's inside. So, quick way to do so is to just type Python 3 and itertools, and normally this will bring you to the description of the package within the first one or two hits. And now you see all the functions that are available in this module, and here is our permutations function that we have used before. Okay. Now, if we only need the permutations function, we can tell Python not to import everything, but just this one. And the way it's done is to use the from keyword together with the import keyword. So we can as well just type from itertools import permutations, like so. And because we have only imported permutations as a function, we now no longer need to provide the module name where it's from. We can now just call permutations without specifying itertools as the module. Okay, works just as before, does the same thing, but now we have not imported all the other functions that are available in the module. Now, if we want all the functions in a module, we can do something like this. From module name import star. That's equivalent to typing from module name import and then all the objects you want to import, which are all the objects that are available in the package. This is typically not a good idea because first of all, if you want to use all the functions, then it's enough to just import the module and then access all the functions in that module. Secondly, you have absolutely no control about the functions that you are importing. So if I type this here, I have now imported the permutations function into my program and I can use it. It's here. But I might have also imported some other function that I have myself defined in my code. Remember that function names need to be unique within a script. You cannot have two functions with the same name, obviously, because then the interpreter wouldn't know what to do. So let's say in this itertools package there is a function called combinations. If I have in my code a function called combinations as well, then I have a conflict, right? And I wouldn't be sure which of the two functions is being used. So this should typically be avoided. Do not just import all the functions from a module like this. Although you might see this in some of the codes on the web, it's really bad practice. Okay, so this has to be avoided. Any questions so far?
Can a Python module override the core function, like print or?
Yes, that's possible. So you can actually define your own functions. I can define my own print function. Even like this, that would now be a recursive call, very dangerous, right? But let's just define an empty print function like this. And then let's do print 9. All right, I need to take some input arguments. So let's define a function print x, which does nothing. I'm now able to type print 9, it will not print out anything. So that's, of course, highly discouraged, right? Never define your own functions, giving them a name that is already available in the Python language as a command. So that should be avoided, of course, because you see this can now produce a lot of confusion, right? You're trying to print out something, but nothing happens. What has gone wrong here? So this is to be avoided. Right, so that's all about importing modules. if we take many modules and we put them together into one collection, we refer to this as a package. There is a package called SciPy, which stands for Scientific Computing Python Functionalities, which has several modules as part of it, and one of them is called linalg, which stands for linear algebra. Okay, so that's an example of a package called SciPy with its module called linalg, and within this package linalg there are now functions we can use, one of them being the Cholesky factorization of a matrix, for example. So if you're not familiar with Cholesky factorization, that should be discussed in one of the numerical analysis modules here. It is a factorization of a square matrix, which has to be positive definite, into the product of a lower triangular matrix L and its transpose. So L times L transpose should be equal to the matrix A that we have defined, okay, which is symmetric positive definite. Now let's see if we can learn something about this Cholesky function using Python alone. I'm importing the module linalg from SciPy, and now we can use the help function on any function that is part of this module. And that's something very useful. All these packages and modules have help built within them, and that's exactly what the doc strings are used for. So when we type help here, what is being printed out is the doc string of the Cholesky function, and it gives you all the information that you need in order to use it. So here is the definition of the function. These are the input arguments. It takes 4 input arguments, and there's a short description of what this function is doing. It computes the Cholesky decomposition of a matrix, and here is a description of all the input parameters. In particular, A is an array-like object, which represents a matrix in this case, and then the other parameters have some description given here. Okay. These are the input parameters. What are the outputs? The outputs are arrays. In this case, it's called C. And what exceptions are raised by this module? Well, there is an exception called linalg error, which is an exception that appears when the decomposition fails for one reason. Okay? And this is how a good doc string should look like for any function. It specifies shortly what this function does. It tells us what are the input parameters and their type. It tells us what are the outputs, and it also lets us know what potential errors can be raised by this function. And then, what is even better, there are some examples that we can just copy and paste and try out. So here is some code which would define a 2 by 2 matrix. And I will talk a bit more about NP later on, so don't worry about this. All this does here is it defines a matrix. And then here I'm calling the Cholesky function on this matrix. And the output of this Cholesky function will be L, which is one of the factors that we have computed. So here is this program in action. I've defined a 2 by 2 matrix with entries 1, minus 2i, 2i, and 5. This turns out to be a positive definite matrix. And the factors that are computed by the linalg Cholesky function are printed out here. You see there are 2 by 2 dimensional arrays, which are matrices, and the entries are printed out here as well. How have I learned about the existence of this function? The short answer is using Google, right? So if you just Google Python 3 Cholesky factorization, then the first hit that you will find is exactly that function. And it's almost as easy as copying and pasting this example code which is provided on the website. So it is in fact very easy to make use of functions that other people have provided for us. Okay, so can we actually make our own modules and give them away to other people? Would be nice, right? So if we're using other people's work, maybe we should also contribute to the Python language by providing our own functions. So we want to make our own module. And at first thought, this seems to be a very advanced concept, right? We are now going to extend an existing programming language ourselves. Isn't this quite difficult? It turns out it is actually very easy in Python. And I want to demonstrate this at an example. So let's say we have gone through the trouble of writing our own prime factorizations function. Maybe that was part of one of the tests previously. So what we have here are two functions. One is called isPrime, that just returns true when a number is a prime number and false otherwise. And then we have written this generator here called prime factors, which takes as input some number n, and then it returns, it's a generator, so it will yield all the prime factors one after the other. We can use it. Just to demonstrate, let me save this as primefactors.py. And note that I'm avoiding any spaces here, so the file name should not have any spaces in them, and you will see in a second why this is the case. So I'm going to save this, and I'm just running it. And the code is done so that there is an input command in the main part of the code, which we should typically avoid, but now it's here. So we actually have to input something. Let's say n is 182. And now we have a big problem because I have previously overwritten the print command, you remember? That's still active in my in this console here. So this console that I'm running here still has a prime function being defined, which does not print out anything. So in order to get rid of this, I need to restart the kernel, which means that this predefined function will be lost and it will be reloaded with the actual print function that is available in Python. So let's try again. Input 182, and there we are. The print command is working again, and it's printing out the 3 prime factors of that number, 2, 7, and 13. All right, so that's a nice module. I want to now give this to someone else so they can compute prime factors for their own numbers within their own code. How can I do this? All I have to do is I have to give this Python script that we have written to someone else, and they can just type import prime factors. From this moment on, prime factors will be available as a module, and they can just use all the functions in it. Because prime factors is quite long, I will import it as pf. And now I can type pf. And you see that Spider is quite clever. It already, as soon as I type the dot, it shows me all the functions that are available in the module. So there is, in fact, a prime factors function, which I can now use like so. Mind you that this module needs to be in the same folder as my script. So the script, my main program, is called lecture8.py, and the module is in the same folder. It's called prime_factors.py. Now, if my module had a space in it, I would have to type something like this, right? And now Python would complain it doesn't like module names that have spaces in them. That's why it's important to avoid them when we save our Python scripts as modules. So let's test this. Let's just run it. Okay, so someone gave me this prime factors module and told me that there is a prime factors function in it, which I can just call to get all the prime factors. But now I have imported this module, and annoyingly, it's now asking me for some input n, which I never asked for, right? So this is why I told you all the time you should not have any code outside any functions. Because when I import a script as a module, everything that is not inside a function will be executed as soon as you import that module, right? Which is typically unwanted behavior. So we don't want this. I mean, I can now type something here and it will do as intended. We need to avoid putting any code outside functions because we do not want this to be executed when we import it. So let's get rid of this input that we had there. Save again. and run this code from scratch. And it's now actually working. Python tells me that I have previously loaded this module. I don't need to load it again technically, but it doesn't really matter, so I can reload modules as often as I want. This computation now works, and I can verify this by printing out the prime factors that are returned by that iterator. But of course, I first need to convert them into a list, because prime factors is only a generator, right? So let's call the prime factors function within the PF module, convert the generated numbers into a list, and print out that list. And here we are. So this is now a useful module that can be used by someone else. We just give it away. Okay, that's good. Sometimes there is, in fact, some code in the main program that we want to be executed when we run this code, not as a module, but as a main script. So here is the same two functions again, is prime and prime factors. And here is a small trick that you can use for yourself if you want. When a Python script is being executed, there is a special variable which is called __name__, right? So you see there are two underscores here, then name, and then ___. This is a special variable that is defined for you. You don't need to define it yourself. And this variable takes a special value, which is a string of this form, __main__, if and only if I'm running this module on its own without being imported by another program. So when I take this module here that I've written before, and I hit execute, its name will be main, and therefore what I've written here will actually be run. Okay, so we can just try this out. I'm executing this, and indeed it's asking me for n, and as before it's computing the prime factors. However, when I take this module and I only import it from another script, I'm not asked for inputting anything, because this part is not being executed. Okay, so that's a very useful trick to distinguish whether your function is, or your module is executed by itself, by hitting execute directly from the module, or whether it is imported into another program. Okay. So when is this used? This is used if you have some testing code in your module that you do not want to remove, but you want to keep it in, but it should not be executed when somebody else is using your module. It is also used when you have some kind of initialization that is necessary. For example, if you write a module that crawls the internet for websites, one after the other, and returns websites as a generator, you might have some part in your module where you initialize the internet connection that you need for your script, right? So some kind of initialization might go into this part here as well. So just a summary, this variable is a special one. It will have a value which is a string called main when this function is called as a main program. Otherwise, the string will contain the name of the module of the program that imports it. Okay, we can just print out the value of the variable name like so, and then run our lecture 8 script. And what you see here is the name is now not main, it's called prime factors, because this script is now being executed as a module called prime factors. This here is from the print command that we have just typed in. A quick summary, it is good to have no code in the main part of your module, except it corresponds to some initialization. So if your module, for example, needs a certain user code for establishing an email connection or internet connection, you might have this as part of your main program. Otherwise, everything should be contained in functions. So let's have a look at some of the modules that come with Python. The most basic one is the sys module, which provides some system-specific constants and functions. So what does this mean? It means that if you use the sys module to, for example, get the names of the modules that are installed on a computer, there's a function called modules that does exactly this. This will work on a Windows machine. It should also work on a Mac and on a Linux computer. Right? So this system module should work cross-platform. That's how it's called. It should actually work in any computing environments. So here are some examples. We can import a function called stdout and stdr from the sys module. And once this is available, we can write stuff to the standard output of your Python script. So what this does in this particular case is the same as print. It will just print something to the console. So we get 3 outputs here. The first one is this one here. This is the same as print. It has been produced by calling stdout.write. stdout stands for the standard output of the Python script. Okay, so you're writing something to the standard output, and the standard output in this example is the console. Why do we need this function? Well, it turns out that you can actually change the standard output of your Python script. For example, you might want your script to print everything that it produces to a printer. So stdout can be changed to anything you want. It can be a printer, it can be a connection to an email server, so you can have all the outputs of your Python script being emailed to someone. It can be uploaded to a web server and so on, right? So that's what this stdout stands for. In general, when you use it out of the box, it is just printing everything to the console, but it doesn't need to. It can also output data somewhere else. You might have seen this before. If you have an error in your Python script, the error message when the program stops always appears at the end. So this is now actually printed after the script has finished. We get the output from the error messages, and that's what we have written to stdr. And here is a constant in the systems package called path, which stores the information where all your Python modules are located on the computer. So apparently on this machine here, I have some Python packages available in the directory users, my username, and IPython. And I have some others available in Anaconda, lib, /site packages, and so on. That's a very technical issue. It's usually not necessary to look at the path yourself. But if you want to know where your modules are located, you can just print the value of sys.path. It should tell you exactly where you can find your Python modules. Okay. In IPython, which I'm actually using to print these lecture notes, stdr is printed out with a red underlying warning color, so it tells me that this was an error message, right? That's the difference between stdout and stdr. It's very nicely visualized in IPython. Not so much in Spider. That's the systems package. If you want to learn more about it, again, there is a very long list of all the functions that are available. Let's move on to another one, the package OS. OS stands for operating system. In my case, it would be a Windows machine. You might have a Mac. Doesn't really matter. This package provides us with functions that, again, will work independently of whether you're using a Windows machine or a Mac. Okay, so these functions should work cross-platform. And there is a whole selection of functions available. For example, get cwd, which stands for get the current working directory. Remember, when we execute functions or scripts in Spider, then we are located in a certain folder on our machine. So for example, if I want to open a file for reading, it needs to be in the same location as my Python script. What is this location? How can I find out what the current location of my script is? Well, to this end, there is a get current working directory function. So let's try this one out. import OS, and now I have this function, and I'm printing the current working directory, and it turns out to be my home directory, desktop /Python. Right? That's exactly this folder on my desktop, which is called Python. That's the location of my script. A very useful module is the time module, which has many functions related to times and time zones. For example, we can get the time in seconds that has passed since the 1st of January 1970 using the time function in that package. So let's try this. There's a function called time inside the time module, which I'm importing. I'm also importing the floor and sqrt function from the mathematics package. We have used them before. And what I want to do now is I want to get the current time. This will be, st will be a floating point number corresponding to the seconds since 1970. So quite a big number. I then want to perform a computation, namely computing the prime factors of a number. And then I want to get the current time again, which will be, of course, a bit later, right? Because this computation will have taken some time. If I then take the difference of time and the one that we have measured here, I should get the difference in seconds that have passed between line 10 and line 12. This should give us an idea of how long our function has computed. Now, this prime factors function is not available yet. I need to make it available and run the script. So let's compute the prime factors of 318. Here they are, 2, 3, and 53. And the time that has passed in seconds is 0.000 seconds. So that's obviously too easy for our prime factors function. Let's try a bigger number. 1, 2, 3, 4, 5, 6, 7, 8. All right, so this took about 1 second. Now we can actually see something. And here are the prime factors of this rather large number. Right? So when is this useful? Well, every time you want to work with times, you want to, for example, print out the current time to the console, or if you want to measure how efficient your functions are, the time method is very useful for that. Another thing that I would like to mention is in terms of timings, when you run a script several times, you will get different timings. So let's just compute again the prime factors of this number. 1, 2, 3, 4, 5, 6, 7, 8. You see, now it was actually slightly faster. It's only a matter of milliseconds faster, but it's not the same number. Right? This has to do with the fact that your computer is doing many other things at the same time, right? You're not just running your Python script. Your operating system is maybe doing some backups on the hard drive in the meantime. Maybe your email program is currently downloading some emails. All of this influences the execution time of your script because they all share the same processors. So typically when doing timings, it is recommended to average. And the simple trick of doing this is to say, I have maybe a for loop like this, and I'm going to run the same thing, let's say 10 times. And of course, if I do this, in order to be fair, I need to then divide the total time that I have computed by 10, right, after 10 runs. So now we should get something that is a little bit more robust with respect to measurements. I try a slightly smaller number now because it takes too long otherwise. Okay, well, 10 times was good enough at least to get 2 significant digits of the seconds more or less reliably, right? So do multiple runs of the same thing if you want to be more or less sure about the execution time of a function. The time package also contains useful functions for converting strings to timestamps and timestamps to strings. So you remember this one function that we wrote previously where we give it a string and it has to find actually 2 strings, it has to find the difference between these in terms of whether one came earlier than the other. This can actually be done very easily using the corresponding functions from the time module. You don't need to do this yourself in the future. Okay, the random module is an interesting one. It allows us to generate numbers that behave like random numbers, right? So it's very easy to use. There is a function called uniform within the random package, and once you have imported it, you can generate random numbers between, let's say, 17 and 19. So that's what this simple code here does. Here are some pseudo-random numbers. Why are they called pseudo-random? Because computers cannot really generate random numbers, right? Everything that they do is deterministic. So what goes on here really is a very complicated algorithm, or a seemingly very complicated algorithm, that generates numbers one after the other, and they have the property of appearing to be almost random, but they are really not. And you can in fact see this if you initialize the random number generator with a seed, with the function seed, which is also available in this random package, then you can generate the same sequence of random numbers over and over again. So I'm initializing the random number generator using this seed, let's say 17. I get 5 numbers, which look pretty random to me. But then when I reinitialize the seed, I get exactly the same type of random numbers. Okay, so they are not actually random, because it's impossible to regenerate random numbers. If I can regenerate them, they are no longer random, right? But for all practical purposes, the numbers that come out here, they behave as if they were random and uniformly distributed in the interval 17, 19. Okay, so there's a long list. I just highlight a few more. So we have already used the mathematics and complex mathematics packages before for computing square roots and powers and logarithms. They have the same functions. The only difference is that CMath can deal with complex numbers. So whenever you need complex numbers, then use the CMath package. And then there is the SciPy package, which has many modules for us, namely the NumPy module, matplotlib, SymPy, and so on. I will talk about pandas next week, because that's the module we use for data analysis. Okay, it's a very powerful package that allows us to do lots of calculations on high-dimensional data, including time series, for example. And maybe another one I would like to highlight here is matplotlib, which is a package for plotting. So far, what we have done has only been on the console in Python. We have not produced any graphics, right? But we can actually do this very quickly using matplotlib. I just show you an example and talk you through it quickly. I hope it's installed on this machine. Okay, the first time you're loading a package, it can take some time because it has to import all the functions available to us. So matplotlib is the library, and one part of this library is pyplot, which is typically imported as PLT. That's a convention. So if you look online for codes that do some plotting, PLT is universal. Everybody calls this package PLT when they refer to it. And what you can do with this is quite neat. So you can define a list of numbers using, for example, a generator expression like this, right? So that's just a list of numbers between minus 10 times pi and plus 10 times pi. And I'm using about 1,000 points in this list. I call it domain. And I have another list which corresponds to the absolute modulus of a number raised to the power 1.5 multiplied by sign. So that's just another list which is generated using the previous one with the corresponding function values. And now in order to plot this function, all I have to do is I have to access the plot function from the pyplot package called PLT. I give it the domain, which are the x values, and the image, which are the y values. And we can, for example, plot with a purple color, like so. And that's what you get, right? So this is how easy it is in Python to produce plots. And you might actually recognize the syntax. For example, x label and y label and title is very close to MATLAB's syntax for plotting. If you have ever used MATLAB, you should find it very easy to get going with pyplot in the future and produce graphs there. If you're interested, there's a long list of some other packages like NumPy and also the statistics package. I have some examples here. It's not very useful for me to talk you through this because you will not remember all of this by just seeing it. You have to really read it yourself, right? So I encourage you to read through this and play with the codes that are provided in these lecture notes.